Deepak. Just want to make sure everyone can hear.
Yes, we can.
Yeah.
Okay, great. So first of all, thank you for inviting us to come and speak with the group today. I'm going to start with a few remarks about MISO before handing it off to Matt to describe the work in a bit more detail. First slide, please, Matt. So for the Midcontinent Independent System Operator, we are tasked with 3 major activities: operating the power grid, managing the energy markets, and planning the future grid. Our footprint covers 15 US states and the Canadian province of Manitoba. We oversee about $40 billion in annual market transactions. The generation fleet has more than 6,800 units with a capacity totaling around 190 gigawatts. And that's compared to our historical peak load at about 125 gigawatts. We are planning and operating 68,000 miles of transmission lines. And among our members and market participants, we have more than 190 member utilities, more than 500 market participants, which means at the end of the day, we are serving approximately 45 million people. In 2022, you can see down on the lower right-hand side of the slide, about 17% of our annual energy came from renewables. Next slide, please. But we are anticipating that the amount of renewables and inverter-based resources more broadly will rapidly increase on the MISO system over the next 15 years or so. So right now we are seeing that we could approach about 30% of our annual energy from renewables within 5 years. And our current estimates based on our member plans show us hitting the 50% mark of annual energy from renewables around 2036. It's worth noting those 2 studies do not include transmission assumptions and are more of a resource forecasting look. In 2021, we published a study called the Renewable Integration Impact Assessment, or RIA. And that was a study where we dove into the complexities of reaching different milestones of annual renewable energy penetration. And that's what the figure here on the right is related to. For the 50% milestone, we saw instantaneous penetration of around 90%. And in this study, we actually performed steady state and dynamics studies on those cases with nearly 90% instantaneous penetration. We have another study called the Regional Resource Assessment, or RRA, which is where we collect our members' plans and goals. And this is where we're getting the suggested timing for when MISO might achieve these different levels of annual renewable penetration. So based on the RRA, we are seeing that the 50% point could be reached within the next 15 years. Of course, like all predictions, this timing is based on a number of additional assumptions. The first is that all of our members and states' decarbonization plans come to fruition at the announced times, that these decarbonization goals are met with a mix of solar, hybrid, wind, and nuclear. It also depends on whether all the needed capacity can make it through the interconnection queue at the appropriate times, and furthermore, that in-service dates are not delayed due to supply chain issues. To achieve that 50% of annual energy from renewables, we are projecting around 160 gigawatts of new nameplate capacity is needed on the system. That's almost equal to what our current nameplate capacity is. As of February 2023, the MISO queue is about 265 gigawatts, and over 95% of the 2022 queue submissions are inverter-based resources. So we're expecting to have quite a high concentration of inverter-based resources on our system coming into service over the next decade or so. When we couple that with traditional resources retiring, we are expecting to see a reduction in reliability attributes. And in order to operate and plan the power system, we are responsible for maintaining reliability through this energy transition. And to help us do so, and to help us continue to do so, we've begun a study into attributes. Next slide, please, Matt. So in 2023, our attribute work is going to be focused on developing quantitative metrics, understanding current and predicted contributions, and constructing a roadmap to assist members in resource planning and prioritizing the appropriate market mechanisms. This year, we will focus on availability, fuel assurance, long duration energy at high output, rapid startup, ramp up capability, and what we really wanted to share with you today, voltage stability. Other essential reliability attributes could include voltage support, frequency support, protection enablement, and recovery and restoration. All of these are topics that UNIFI is working on, so we're very pleased to be participating in the consortium and are excited to continue to learn more about how advanced inverters may be able to supply attributes into the future. So although something like inertia or fast frequency response, which have come up quite a bit in these weekly seminars, could also be considered essential reliability services, for the near term, our focus is on voltage stability. And this is primarily due to the findings from RIA, that renewable energy milestone study that we just talked about. And in that work, we saw long transfers from weak grids were increasingly important at higher and higher renewable penetrations. We've been working with Telos and Hickory Ledge to help us evaluate voltage stability. So I'll now turn it over to Matt to introduce the problem and the work that they've been doing. Thank you very much.
Thanks, Hilary. And hello, everyone. Thanks for the great setup and the context. Those numbers in the MISO territory, every time I hear them, it's just really big numbers. It's very ambitious. It's really exciting to see. I'm very excited to share some of this work with all of you, and I want to acknowledge a few of our great partners here. MISO, of course, being one of them. Also, my colleague Nick Miller and his company Hickory Ledge, and as well as to acknowledge Rick O'Connell and the folks at Grid Lab who provided some early support for us in getting into and understanding this. And thank you to the UNIFI team for having me. And, I don't want to belabor the point. I think Hilary did an excellent job setting up, and MISO's been paying a lot of attention to this for many years now and doing a lot of great study work around long-range planning, in which the idea is to consider a very large scenario set. There's naturally a lot of uncertainty in these time horizons. And what we do know is there definitely a high inverter future appears on the horizon. But there's a lot of cases exactly what that technology looks like, where it goes across the MISO footprint. All of those things in different pockets have different implications for system stability, in particular voltage stability. Couple that with the practical challenges to modeling inverters. I think for this audience and the folks are well aware of these. There's we have different sets of tools, and we'll talk a little bit more about this. And each of those tools have their own challenge. And in doing all of that, the technology is quickly evolving. And we're, of course, the focus here being grid forming inverter technology is, front and center. So something that's aware of us, that's right in front of us today. And so what do we do? Okay, so don't panic. And for the folks that know me, I mean, that was actually not a picture of me, but I like to put it up there because I've been accused of being that person, Macaulay Culkin. But it's something. Yeah. So jumping into, I love telling jokes to a to a webinar muted format. It's completely open loop. So bear with me. I'm just going to imagine everybody is quietly giggling. Getting into some of the motivation behind what we're looking at. So if we think about the tools that we use and just drawing kind of big picture, level of detail versus burden. And the burden being not just the computational burden and how many cores are you throwing at the problem, but also the people burden, the people problem. And in terms of having the technical talent, not just to set up the models and use them, but also to digest and interpret and draw meaningful conclusions from mountains of data and wiggles. It's substantial. And so if we look at on the bottom left, a steady state, and this isn't often, maybe it's not always tied into stability challenges, but we really wanted to put this on the map because If you think about steady state in terms of kind of the voltage stability aspect and drawing the PV curves of the system and seeing how that as the power transfer levels increase, what happens to the voltages across the transmission system. And so the level of detail, you're not doing time series runs, you're not doing dynamics. And so you've got, maybe you're missing something, missing a number of things in terms of low level of detail, but it is relatively low burden, and you can study large systems, and therefore you can study lots of it. You can do that quickly, and you can look at lots of variations and lots of sensitivities on that. And so while the level of detail is low, the burden is also low, which allows you to cover a lot of ground. We go up a step from that into the world of positive sequence dynamics, where now we have time series simulations. We have generally the generic models being at the forefront of those, but also user dynamic models, or excuse me, user written dynamic models. You're able to incorporate more detail there, but they're still making simplifications and assumptions. And so you've got a step up in detail, but also you've got a step up in burden. These models take longer to run. There's plenty of initialization issues that you can have along the way. And so you're forced to be a little bit more choosy about the types of scenarios you study with those. And then finally, when we step all the way up into the electromagnetic transients, the maximum level of detail that we have in a simulation environment, and similarly, a lot of burden in terms of computational power and the people that are acquainted with these tools and able to use them effectively and digest those results. And so when we see it in this way, one thing that occurred to us is that there's a gap in this layout. And our area of focus has been at addressing the gap in terms of, is there a method and a tool, if you will, that fits in between, somewhere in between the steady state and the positive sequence dynamics range, where you have some detail, more than you would expect in steady state, maybe not so much as positive sequence dynamics, and certainly not as much as you would get in an EMT type simulation, but where you could still keep the burden low, and low enough to run a lot of cases and to look at and cover a lot of ground and try to understand what the uncertainty is in these different snapshots in terms of where the technology is going and how much on the system. Something that we see as particularly important when trying to plan a system the size of MISOs, or really any large system, where you'll never get to the perfect answer, for instance, because you'll never know with zero uncertainty what to set up. And so how do you cover a lot of ground quickly and screen and understand where you want to be applying the tools, the kind of the bigger hammers like positive sequence dynamics and electromagnetic transient simulation. So now into the stability. The focus, as Hilary mentioned, the near-term focus here is in dynamic stability. And why start here? There's many aspects that have been covered here about stability. Well, it's important for all power systems, especially large systems with long lines. We're focused here on balanced systems, so positive sequence behaviors. And one of the key reasons why we're focusing on the dynamic voltage stability is because it's kind of one kernel of the weak grid problem. And so where you have the high levels of penetrations in IBR, commonly described as the weak grid, as presenting a weak grid challenge. That's one of the big points that we see. We're not focused right now on frequency stability or the inertia or kind of that short-term active power response, though it's a close adjacency. But considering those as separate for now, we're not looking at unbalanced or asymmetric disturbances in this effort either. Not to say that those aren't really important and relevant, it's just not the focus of this work. So to get into the voltage stability, and I know we have a lot of folks that have been in tremendous depth on these presentations throughout UNIFI. But just to pick this up and where everyone is, I think, or on voltage stability and grid strength, I like to use an analogy, return to an analogy with a trampoline that's been around for several years, and I still like it. If you consider the transmission system voltages as the trampoline, or kind of the canvas part of a trampoline, and you consider it supported by a number of springs to a rail, to a metal frame that's providing kind of the voltage anchors. So what you would see, the trampoline being the transmission system voltages, and in kind of normal conditions, it's flat. All of the voltages are well supported, and they are supported to a voltage anchor, which would conventionally be a large synchronous machine through a tie line. As we proceed here and we get to a weaker system, weakening grids, conventionally what that's meant is we're displacing synchronous machines, we're retiring or decommitting the synchronous machines, which looks like we're disconnecting our trampoline in places from its voltage anchor. And so now you can imagine comparing, if you apply a load to the transmission system, you expect some voltage drop, you expect some deflection in the trampoline. When you disconnect more of these machines, when you disconnect the springs from the metal rail, you would expect more deflection in the trampoline as well. Okay, so that's where the analogy started. And now I want to extend it a little bit further. And this analogy is by no means perfect, but I think it gets to illustrating a key point. So the steel frame of the trampoline is more or less an idealized condition. What we'd really have is resources of different sizes. And for instance, for the moment, considering synchronous machines, you can have large synchronous machines or small synchronous machines. And so in the case where you have large synchronous machines, I'm going to draw on some help from my friends Spike and Chester, the cartoons. So Spike being a big resource or a large synchronous machine, he'd be coupled to the grid through a relatively short transmission line or this big stiff spring. And the result would be in that region, you would expect to have a strong grid because you have a big resource and a big transmission line, or kind of a short transmission line. In contrast, you could have a small resource there. And so Chester, not quite as big and robust as Spike, tied to the grid via a relatively short transmission line. But in that area, you can have a weak grid because of that small resource, in spite of having the substantial transmission. And then kind of blending those two together, you can also have a weak grid issue if you have that big sturdy resource, but if it's separated by a long transmission line, or the place in the grid that you're looking is far away from that resource, then you can also have a weak grid condition in that area. And so if you'll bear with me, I want to extend this analogy further still to voltage stability and to controls. And so if we consider just the large resource coupled to the grid fairly strongly by the transmission system being our short, stiff spring, we'd have a strong grid with a big resource, a big transmission line, and immediate response. And the top, Spike is alert. He's at the ready, and he's holding that spring firm. And for any changes that might happen on the system, they're going to be, Spike is immediately going to be providing support for that. In contrast, if Spike is a little bit off the clock, he's a little bit, befuddled, and he's not really paying attention to what's happening, you can have that big resource, you can have it strongly coupled to the grid, but if an event happens and it takes a second to get a response out of that resource, then you can also have a weak grid problem because of a delayed or a small or inadequate response, even if the resource is big, even if the transmission system is really strong in that area. And so what this boils down to is, to us, it's the quality of voltage regulation that matters for voltage stability. And so if you think about when we're talking about voltage stability and grid strength, we've customarily been focused on metrics like the short circuit strength or the short circuit ratio. And that accounts for some pieces of it, but it doesn't necessarily account for the quality of the voltage regulation that's being provided. And by quality, I mean, how much effort are you applying? And how quickly are you applying that effort? And so those two things, you like a significant response, a lot of effort to be applied to being able to hold those voltages constant, especially as a dynamic event happens. And you want to respond quickly. But as we know, that's not just simply a matter of turning up the gains on your control system. Usually, if you take that approach, you quickly find that you pay the price in damping and trade it off with the damping. And so that is another aspect of this that I want to acknowledge, though it's not a core focus of this work presenting here today. So how do we characterize the resources to be, do we have a spike? Do we have a Chester? How alert is spike, right? What is the quality of the voltage regulation? And so one approach that we've taken, and there are many, is to characterize the relationship by looking at the response of a resource, i.e. the current it is exchanging in response to a dynamic event or a changing voltage. And so setting this up for those more mathematically minded, if we look at the input being a voltage phasor with a magnitude and an angle, mapping that through a matrix and having the result being the current at the terminals of the resource in the DQ domain. And so you have a matrix with the four parts, so the four elements, where I'll just go one by one quickly. So Y11 here is essentially the relationship between the reactive current and the voltage magnitude. And this is really the focus of what I'll be sharing today. It's that volt-var relationship where when the voltage magnitude changes, you expect a response in reactive current. So for instance, if voltage suddenly drops for some change out on the grid, you would expect a voltage supporting response to try to restore voltage, which would mean an injection of reactive power and consequently reactive current, or the conjugate of that. You can also have a relationship between voltage magnitude and between the voltage angle and the reactive current. This isn't normally what we think of, and so I'm kind of referring to it as a cross term, which I expect, and generally I found it to be pretty small. On the other end, you can have a relationship between voltage magnitude and active current. Again, what I would be considering a cross term, we don't normally think of that relationship as being a dominant factor. And then, and I made a typo, forgive me there, this should be Y22, the relationship between voltage angle and active current. And this is more of that inertial relationship where when an event happens, frequency starts moving, really the angle is moving, and you would expect a corrective action, or you would hope for some resources will provide a corrective action in terms of their active current response. There's a lot of really great work that I've seen kind of setting up this type of characterization. Shahil, Shah, Enrel, for instance, is just one of several people I know exploring this area, and I think doing really great work in kind of the impedance space and the frequency domain. So why do we like this characterization? A few reasons. One, it's a relatively simple indicator of performance. It's relatively easy to understand. I think short circuit ratio is one of those where it's not perfect, but its strength is that it's relatively easy to understand. And now I think as we're pushing the limits of where short circuit ratio can be useful, we need to look for something else to capture that performance. And I look in this direction. While it's maybe not as simple, it still has some of that simplicity aspect of it, but can capture more of the characteristics, more of that quality of voltage regulation. It acknowledges the complexity of the behavior. So we'll share that, we're generating this in a frequency domain, and we'll be sharing a plot of that. But while I'm not attempting to capture everything that's relevant or important, we are showing it in some complexity to provide that appreciation. It's repeatable, it's scalable. So this approach of characterizing resources like this can be applied to any voltage regulating resource. It's technology agnostic, and you could just set it up and do the same thing for any resource for which you have a suitable model. So in that sense, it's technology agnostic as well. It levels the playing field. You can compare the results of different technologies, of different types of resources, of different tunings. You can compare them relatively quickly and get a picture of the quality of their voltage regulation performance, relatively easily. And it's extendable. And so while we are focused on the voltage stability aspect of this, the matrix that I just shared, in which you're looking for relationships potentially between voltage angle and active current, it works similarly. You can create similar characterizations on the active power side. It's just right now we're focused on the reactive power side. And so to share what this is, how are we looking at this? I want to kind of merge, our cartoons with some real numbers and some real results that we've been seeing. So first, on the x-axis, we're showing frequency. So this is the result of, we're presenting the results in the frequency domain. And frequency here, I'm showing in hertz, and it's in the rotor reference frame. On the y-axis, I'm showing our grid strengthening metric, where it's really the resource's internal admittance. And so for high admittances or low impedances to your voltage source, you end up looking more like spike, or you have a big resource. And conversely on Chester for lower admittances or lower grid strengthening values. And I've shown just 3 curves here. And these curves are based on the results of detailed models and that were produced from time domain simulations and EMT. And then through a number of post-processing to get it in a view like this. And so I'll start with the red trace, the synchronous machine trace. And as a familiar reference for how our systems operate, I like to have that as a comparison. And you can see as the admittance is increasing with frequency, that's what we would expect, though maybe we're normally used to thinking about it in different domains. I think most folks would think about it if as largely an inductance, where the reactance would increase as a function of electrical frequency or stator reference frame. So when you make those 2 translations in your mind to rotor reference frame and to admittance, again, you get generally an increasing line. What we see on the next resource is in green, grid following inverter resource. And I'll just point out a couple things about that. So one, it's generally showing a lower admittance than that of a synchronous machine. That is something that I think is not a surprise. It's what we expect. We know that grid following inverters do not support the grid in the same way that a synchronous machine would. And particularly that's true around voltage regulation. What I will note is that it ticks up at the low frequency range. And so, for instance, this inverter was modeled with terminal voltage regulation. And that's why for relatively low frequencies where terminal voltage regulation has a finite band, that's what's showing up here. And that at very low frequencies, it's able to follow its voltage reference and help regulate voltage at the terminals. For faster dynamic events, that you move outside of the voltage regulator's bandwidth and you don't get much of a useful response. And then finally, with grid forming inverters, an example grid forming inverter shown in purple. One of the things that you notice is first, the admittance value, the grid strengthening behavior is significantly higher than both the grid following inverter, which we would expect, but also even the synchronous machine example in this case. And second, the response is relatively constant across this portion of the frequency domain. And so what we see here is that the grid forming inverter is supporting voltage. It's applying a fair amount of effort, and it's also doing that in kind of all of the relevant timeframes that I would consider for kind of the large system stability. And so this shows that the quality of voltage regulation from, for instance, this example grid forming inverter is higher than that of this example synchronous machine and this example grid following inverter. So there are many steps of getting from time domain simulations in EMT to this that I don't have time to get into here and now, but happy to entertain those. The last thing I wanted to point out is this orange shaded portion of the curve, 2 to 10 hertz in the frequency domain, or roughly 100 milliseconds to 500 milliseconds when thought about in the time domain, after the disturbance. That is a kind of an empirical view of what's the critical band that is important for voltage stability on the system. Like where in this frequency domain should we be paying the most attention, particularly when the value is not constant across the frequency domain. And so I've seen, and our empirical results indicate that it's those first couple hundred milliseconds after the event of can you control voltage in that time? And so that's why I've highlighted it here in the frequency domain. So,
hey, Matt.
Yes.
Quick 10-minute time check.
Thank you, Deepak. So once we have this resource characterization, those plots in the frequency domain, what can we do about that? And so I'd like to return here to our familiar Thevenin equivalent, in which we have a resource model represented by an ideal voltage source and an impedance, something that we're very accustomed to doing. But the impedance that we use can now be set according to the actual behavior of a resource when characterized in the way that I just described. So for instance, if you consider a spike-like resource, a large alert resource with a high admittance, internal admittance, or high grid strengthening capability, the reciprocal of that being a low impedance, which would mean that the rest of your system, or really the terminals, are closely electrically coupled to an ideal voltage source. So this resource model would have more of those ideal voltage source characteristics. Conversely, poor grid strengthening resources, whether they're small or are not playing a role in the relevant time periods where the response is expected and needed, would have a low admittance or a higher impedance. And so in that way, the terminals of the resource are farther away electrically from the ideal voltage source representation. And so in this way, we can beef up our relatively simple Thevenin equivalent models to reflect the quality of voltage regulation and assess how that behaves on the larger system. And so what we're doing is we've been using a simplified system for testing this concept. And without going into too much detail here, we have a relatively simple but still networked large system representation with 6 places for resources. And we have a sending end and a sinking end or receiving end. And so power flow is generally flowing from kind of left to right through the simplified network through a number of these paths. Each of these paths being represented as a number of high voltage transmission lines. So it's not, it's simple enough to be manageable for testing in multiple tools, but also the idea being complex enough to capture some of the aspects of very large transmission systems. And so now what we're doing is we're returning to that steady state space that I spoke of in the beginning and looking at the PV, looking at this in a PV analysis lens. And so very briefly, the plots that I'm going to show here are having power on the x-axis or the megawatts transferred from that sending end resource, and then the voltage in per unit. And so as we increase the power transfer level, you see a decline in the voltages on the transmission system, which, familiar with this wrapped all the way around, generating our nose curve. And beyond which beyond which the system is unstable and there's no feasible solution. What I'm showing here is the results of a PV curve for an n-1 contingency event. And here there's no dynamic impedance utilized. So the terminal voltages are controlled by the voltage source. And so in a sense, if you think of the Thevenin equivalent, it's zeroed out in this case in terms of an idealized representation, which is typically how these analyses would be run in steady state. Now, if we introduce that dynamic impedance and we consider 2 of the example resources, on the left in purple, we have a grid following like inverter resource at the sending end. And so the introduction of that dynamic impedance has a pretty substantial impact on the shape of this PV curve, in that for lower levels of active power transfer, you see that voltage is not supported as well. Voltage declines much more quickly. Unlike with a grid forming like resource at the sending end, so just making that substitution at the sending end and rerunning the PV analysis, you see that the grid forming like resource provides much better voltage support and actually enables the system to transfer more active power out of the sending end relative to that grid following like resource. And the big difference here is how well each of these resources are supporting the voltage. Sorry. So looking at how would we use information like this? Well, if you could consider, so inside of both of these curves for the same contingency event, you would expect stable operation. And so that's what's shaded in green. And then somewhere between the end of the nose curve with the dynamic impedance modeled and the end of the nose curve with under kind of an idealized representation, you have some marginally stable operation, or there's some, I'd say still some remaining uncertainty in terms of what you're able to do, but you're able to get a different representation of how much is in the stable green region based on looking at different dynamic impedances associated with different resource performance and those technologies, whether it's grid forming or grid following or what have you. And so here you're able to quickly see for this contingency a substantial increase in the level of megawatt transfer that will be expected using a grid forming like resource rather than a grid following like resource. And this ultimately is reflected in the quality of the voltage regulation. And in large systems, we see it make a big difference. So how do we use this? One of the things that we note is those PV curves, those curves are able to be generated relatively quickly. And you can cover a lot of contingencies, and you can also cover a lot of future scenarios. And so where we see this being used, in particular into the integration in existing processes, is shown in blue on the top half. You have your typical steady state contingency analysis where you've defined your scenarios with resource mixes and assumptions of resource mixes, transmission investments, and you have your contingency list, both generation and transmission, and you run it through a steady state analysis tool like PowerGEM's Terra, for instance. Well, now, instead of having all of these resources appear identical and idealized, identical except maybe for the rating, but having that idealized voltage regulating characteristic, we can now introduce a dynamic impedance to capture that, which we would be deriving from detailed resource models through electromagnetic transient simulation, for instance, in PSCAD, resources of grid following, grid forming inverters, StatComs, you name it, whatever it is. It doesn't matter what label you apply to it, as long as you perform that characterization and are able to generate a representative dynamic impedance that could be fed into this analysis. The output of this would help you identify the stressed conditions, the locations, the types of disturbances or contingencies, and some of the limiting phenomena, which would allow you to basically find that subset of cases that warrants using the more intensive tools like positive sequence dynamic simulation or EMT. And so really we see this as a way to augment the existing process and help you know where to focus and where to apply the limited resources that everyone is challenged in and getting the most out of. And so taking a step back then all the way up to the planning level, when you're looking out into these future cases, particularly these high inverter cases, you now have an additional knob to understand the resource type. And so, for instance, when you look at the system and you say, okay, there's going to be a lot of inverter-based resources, for instance, or synchronous resources in this area and inverter-based resources in that area. And what types of resources are we talking about? Are they grid following type resources or grid forming type resources? And we now know that the difference is substantial. And this approach allows us to capture that and see what are the differences in the ability to transfer power from these different types of resources. And I'll leave it like that. I think I might be 1 minute beyond over time, but.
Thanks, Matt. So And thanks, Hilary. That was great. So we've had a couple of questions come